Topic 6.1, Testing a Claim or Idea with One Sample Hypothesis Testing. The learning objectives are as follows. First, I'll discuss how to generate research questions and hypotheses for these questions. I will then go further to discuss the null and alternative hypotheses. Next, Type 1 and Type 2 errors will be differentiated and the link to alpha level will be discussed. I will then describe two methods for conducting hypothesis testing, the p-value approach and the critical value approach. We will then go through a step-by-step approach to go from hypotheses to decisions. First, let's distinguish between one sample and two sample tests. Please note two sample tests will be discussed in topic 6.2 onwards. So for a one sample test we are comparing our sample mean to our hypothesized population parameter, which I often think of as a benchmark value. For example, is the average commuting time to work for those employees living in the metropolitan area and travelling to the CBD less than 32 minutes? Is the average weight of a bag of potato chips equal to 80 grams as stated on the packet? Is the average employee engagement score for our organisation above the industry average of 7? As you can see, these examples only involve the collection of one sample of data and the sample mean is then compared to the benchmark value. This is different to two sample and matched paired tests. Research questions for these tests are more along the lines of, is there a gender pay gap in our organisation, where here we would look at males and females and the average salaries for both. Another question might be, is the weight loss program effective? This is likely to be a before and after study and a paired test. Again, we will discuss these in topic 6.2 onwards. With our hypotheses, we should consider these in terms of pairs. There is a null hypothesis and an alternative hypothesis. The two hypotheses are exhaustive, meaning that they are exact opposites. For the research question about the average time to complete a piece of work, the null hypothesis would be h0 colon mu equals 25 minutes. Note that the hypotheses are always about the population parameters and not about the sample, as we know all about the sample mean, etc., but we are using these sample statistics to understand the unknown population parameters. We always begin with the assumption that the null hypothesis is true. Often, but not always, the null hypothesis refers to the status quo. It always contains the equal sign, albeit less than and equal to, greater than and equal to, or equal to. It may or may not be rejected, but it is never accepted. When it is rejected, this is because there is enough evidence to reject the null hypothesis, but without enough evidence to reject it, this does not mean that we have evidence to accept HO. The alternative hypothesis is the opposite of the null hypothesis, and it's often easier to write this first. For the research question about the average time to complete a piece of work, the alternative hypothesis would be HA, or H1 colon, mu does not equal 25 minutes. The alternative hypothesis never contains the equal sign, but instead will contain a not equal to sign, or a less than sign, or a greater than sign. If we have enough evidence to reject HO, we will then conclude with H1. So in this example, we would conclude that the average time to complete the piece of work is not 25 minutes if we reject HO. In formulating hypotheses, I do not recommend focusing on the status quo because it will become confusing. To help you understand this, think about the last example on the previous slides. In this example, because we were interested in a difference, that is the time to complete the work different to 25 minutes, our hypotheses contain the equals and not equals to in the HO and HA respectively. If, however, we wanted to test whether the time to complete the work is less than 25 minutes, this is referred to as a directional test. In this case, the alternative hypothesis will contain the research question, that is HA colon mu less than 25 minutes, and the null would be HO colon mu greater than or equal to 25 minutes. In this case, working out the hypotheses by considering the status quo doesn't really work. On the slide in front of you, you have other ways for formulating hypotheses. As you can see, we might be considering whether a bag of potato chips has on average 80 grams as stated on the package. In this case, we are testing the status quo. We would test this as a non-directional test with equals and not equals to signs, as we are concerned with both underfilling or overfilling the bags. Underfilling misrepresents the packaging and overfilling leads to wastage and reduced profit. In the second example, a tyre company may want to test whether their tyres last longer than 60,000 kilometres, and they might then use this in their advertising. The 60,000 may be an industry figure, or a figure from a laboratory testing, or perhaps an expert opinion. Either way, we are testing a research hypothesis where the research question is stated in the alternative hypothesis and the null hypothesis states the exact opposite. Now at this point I should stop and say that you're probably thinking the hypotheses are the wrong way around. Please note this is very common when I'm teaching this lecture face to face, but over time and after doing multiple examples you'll hopefully come to understand that this is the only way the hypotheses should be presented. Think about the burden of proof. The only way to prove that the tyres last longer than 60,000 kilometres is to state this in the alternative hypothesis. As we never accept the null, we only accept the alternative hypothesis. Lastly, we have another directional test where the average wait time is hypothesised to be less than 15 minutes. Hence the alternative hypothesis includes this claim about the population. So with hypothesis testing we make one of two decisions. We either reject the null hypothesis or we do not reject the null hypothesis. Please note we never accept the null hypothesis as we can never know the true state of affairs. We only reject it when we have enough evidence to do so, and when we reject it we can then conclude with the alternative hypothesis, as this is the exact opposite of the null. Here are the three main steps to hypothesis testing. First, determine whether the test is about the population mean or the population proportion. In this course we are only discussing the population mean, but once you understand this you can easily apply this to proportional data. Next you need to decide whether you are conducting a directional or non-directional test, that is a one or a two-tailed test. Lastly, set up your hypotheses. As you can see on the slide, the null always contains the equal sign and the alternative never does. Okay, so here's an example for you to work through. A trade group predicts that back-to-school spending will average $606.40 per family this year. So step 1, the parameter of interest is mu, the population mean. We are conducting a non-directional two-tailed test as we are interested in if there is a difference in spending to this figure. The hypotheses are stated as HO colon mu equals $606.40 and HA colon mu does not equal $606.40. So now it's your turn. Please pause the video and develop hypotheses for the two different research questions presented on the slide. When you are done, press play and I will go through the answers. Okay, so to test the research question, is the average back-to-school spend less than $606.40 per family? The null hypothesis is mu is greater than or equal to $606.40, and the alternative hypothesis, which is often easier written first, in this case as it contains the research question, is mu is less than $606.40. Next, to test the research question, is the average back-to-school spend more than $606.40 per family? The null hypothesis is mu is less than or equal to $606.40, and the alternative hypothesis is mu is greater than $606.40. If you got both of those exercises correct, you are on your way. Well done. Okay, so here's the bonus question. Try this one. Again, press pause and see if you can write the hypotheses correctly. The correct hypotheses are HO colon mu equals 32 minutes, H1 colon mu does not equal 32 minutes. This is a deceptively difficult question where we will never truly be able to prove the politician's statement, surprise, surprise. We will only be able to disprove or reject it if the sample evidence shows the mean to be significantly different to 32 minutes. Think that through a little more. If there is evidence that the mean commute time is different to 32 minutes and it's actually found through further testing to be significantly less than 32 minutes, this would delight the politician. But, on the other hand, if the mean commute time is found to be significantly different to 32 minutes and then through further testing is significantly greater than 32 minutes, the politician may not be so happy. The reality is, then, if we do not reject HO in this case, the conclusion would be that there is not enough evidence that the average commute time is different to 32 minutes, which clearly does not prove the statement, but does not reject it either. So now that you are all experts on formulating hypotheses, let's work through a visual example of hypothesis testing. First, let's take the commute time example. In this case, the null hypothesis was HO colon mu equals 32 minutes. We then determine our population. In this case it might be all motorists living in the metropolitan area of Perth and commuting to work by car to the CBD. After defining the population, we then randomly select a sample and compute sample statistics. Suppose the sample mean x bar is 20. With hypothesis testing we are considering whether a sample mean of 20 is likely given a population mean of 32. In this case, we would determine that it is unlikely and reject HO. It is more likely that the population mean is closer to the sample mean of 30. Here is the example using our sampling distribution of the mean. As you know from previous topics, the mean of the sampling distribution is equal to the population mean, and the distribution is normal above certain sample sizes. Have a look at your central limit theory slides if you're not sure about this. So with all of this in mind, it is unlikely, but not impossible, but unlikely, to get a sample mean of 20 if the population mean is 32, and therefore we reject HO on this premise. Okay, so how close is close enough? What do you think? We have to allow for some error in our sample mean due to sampling error or differences from sample to sample. So if we compute a sample mean of 30, does the statement about the population mean of 32 still hold true? I can hear you say probably yes. So then that means 34 would be okay too. So where is the point where the sample mean is too different to support a hypothesized population mean of 32 minutes? Maybe below 24 minutes and above 40 minutes? Maybe you are more stringent than me, or maybe less stringent. There is a grey area here in this example, as we are simply thinking about the exercise without being confused by statistics. But please note, with statistics, there is an exact cut-off point, so rest assured there is no grey area when making decisions about hypothesis testing. In making decisions about the cut-off, you need to consider your alpha level, as type 1 and type 2 errors are related to this. How much type 1 error will you allow? Generally in business research we allow 5%, so this means 5 times in 100 times we will make a type 1 error, or in other words, we will reject the null hypothesis when the null hypothesis is true and should not be rejected. We will not know when we make this error, however on the flip side, 95% of the time we will make the correct decision of rejecting the null hypothesis when it is false and should be rejected. You may ask, well, why not change alpha to 1% and reduce type 1 error even further? Well, the problem here is that this will increase type 2 error of not rejecting the null hypothesis when we should reject it. Look, it's a fine balance. In management research, an alpha level set at 5% is the norm and the value most used throughout this course. Here is a table that usefully points out type 1 and type 2 error. As you can see, when the decision is to reject the null hypothesis and the null hypothesis is true, this is a type 1 error. When the decision is to reject the null hypothesis and the null hypothesis is false, this is a correct decision. When the decision is do not reject the null hypothesis and the null hypothesis is true, this is also a correct decision. Lastly, when the decision is to not reject the null hypothesis and the null hypothesis is false, this is a type 2 error. Okay, I can hear you say, how do we apply this? Here is a legal example which helps to understand hypothesis testing and errors in decisions. In Australia, the burden of proof falls with finding enough evidence to prove someone is guilty, otherwise they are found not guilty. If you live in a different country, this may be different. Anyway, for Australia, because of this, the hypotheses are written as follows: HO: an accused person is innocent, and HA: an accused person is guilty. In this case, a type 1 error occurs when an innocent person is found guilty by the court, and a type 2 error is where a guilty person is deemed not guilty. In the Australian society, type 1 error is considered the worst, and in fact there is a saying by Benjamin Franklin and others that it is better 100 guilty persons should escape than that one innocent person should suffer. Hence, because type 1 error is seen as more costly to society than type 2 error, the alpha level, which is tied to type 1 error, is adjusted accordingly. Lastly, if you read journal articles, you will often see researchers refer to all three standard alpha levels of 1%, 5% and 10%. Your book provides the following interpretations of these alpha levels. Have a look at the slide. Look, I'm not overly excited about this, but they do help to show that a smaller p-value is more convincing. But please note, we should never say that something is very significant or marginally significant, and so on. You'll see this in journal papers quite a lot, but it's actually incorrect. Significance is about a cut-off point, and therefore a finding is either significant or not significant, regardless of how small the p-value is. This is because there are differences from sample to sample, and these will yield different p-values. Lastly, as we are mostly working with a 5% alpha level, the golden rule is that if p is less than 0.05 or 5%, we reject the null hypothesis, otherwise we do not. This rule always holds true regardless of the test. Thank you.